All right, so we talked about this method, and today we're talking about washer method. So we're kind of extending volume into something that's a little bit more involved. All right, so page 13. So this method, the way you can tell that something is this method is, well, first off, we did this example, right, where we have a shaded region, and then we have an axis of revolution. In this case, it was the x-axis. And do you see how the shaded region has a flat surface up against the dotted line? So if you have a flat surface up against the dotted line, that means there's no gap, there's no hole. It's just going to be a complete solid with nothing to subtract out. Okay, so but today we're talking about what if there's a gap? What if there's a hole? What if there's a hollowness to the object? That if that's the case, then we have to subtract something out because it's not the true volume if there's a hollowness to the object. So here's an example of something that has that feature. So let's say, and we're going to do this exact example a little bit later down on the page. But let's say we have this leaf-shaped object that is, hanging out at kind of like a 45-degree angle, and we're rotating this shaded region about the x-axis. Now, notice how this shaded region is touching, but it's not a flat surface, right? It's not up against a flat surface. So as you rotate this, it's going to end up looking like a hollow bowl, right? And that hollowness in the bowl is going to be different than an object that's this, right? We expect these two to have very distinctly different volume. This has a lot more content in this space rather than this one, right? So the volume of this bowl is going to be much less because we're not going to include all that space in the middle. So because of that, we have to think of this as, okay, rather than adding infinitely thin disks, we're going to be adding infinitely thin circular rings, or we call them washers. Okay. But it's still going to be circle related, still going to be pi r squared. But let me do a two-dimensional version of this example. Let's say we have a circle within a circle, or basically a ring. And if I ask you, what would it take for me to find the area of the shaded region? What information will we need? Okay, so you got to find the area or area of the circles, which means I need to find what? What's needed for a circle formula? Radius, right? So I need two radius, right? And then it's basically the radius of the big circle, and then radius of the small circle, and area of the big minus area of the small. So it would be, if I call this big R and little r, big R for the radius of the large circle, and little r for the radius of the small circle, then the area of that circular ring is going to be pi big R squared minus pi little r squared. So basically, we're just going to take this and put integral notation around it, and that will basically accumulate all these infinitely thin circular rings from one end to the other. Right. So with this method, it was just pi big R squared. But then with washer method or circular ring method, it's going to be pi big R squared minus pi little r squared. Okay, so that's really the only thing we have to worry about for this type of problem. We have to end up subtracting out the hollowness or the hole in the object. Okay, Now, before we move on, I do want to point out that, even though it's obvious where the radius is or how to draw the radius from a two-dimensional perspective, sometimes we may get a little bit lost in terms of setting it up, and just to be aware that sometimes we want to do this. Sometimes because we're looking at three-dimensional shape, we may connect the distance between the two graphs and call that the radius. Okay, so just want to make sure that, two-dimensionally, that doesn't make sense, right? We will never call this the radius. The radius has to involve the center of the object. And the center for us is going to be the axis of revolution. So whenever we draw our radius, we have to make sure we extend from we always include the center. We always include the axis of revolution. So you may be tempted to do this because this is how we do area between graphs. We do top graph minus bottom graph, but two-dimensionally, this is never going to be called the radius. All right. So we're going to do this full example below. And again, you're not going to be told, oh, wait, this is this method or this is Washer method. But the way that you can tell is you look at your dotted line versus your shaded region. Okay? If there's a flat surface right up against your dotted line, there's no gap, this method. But if there's a curved surface, or if it's touching, but it's not touching all the way, or if there's a complete gap, then it's going to be Washer method. It's going to be easier for us to create a Washer method situation than this method, because this method has to be a flat surface and has to be up against the dotted line. I think a lot of students do get this confused with this method because they say, well, it's touching, so shouldn't it be this method? But again, it's got to be a flat surface, right? You see all this gap, even though it is touching, there's this, you can imagine, because there's a gap, a hole, not a complete hole, but still a hollow part of the graph, you have to go through a Washer method. All right, so example 1. Find the volume of the solid enclosed by the graph of y equals x squared. That's the parabola that's concave up, that's opening upward. And then y equals root x, that's going to be the radical function that's arching down, revolving around the x-axis. Okay? So there's our axis of revolution. Let's go ahead and draw that dotted line. Again, it's touching the line, but not all the way, right? It's got to be a flat surface in order for it to be this method. So we know this is going to be Washer method. So we're going to be expecting 2 different radius. And because it's Washer method, we have to draw 2 radius to draw 2 radius. I know, again, the axis looks like the edge of the diagram, but it's really the center of the diagram, because this is going to rotate and the bowl is going to end up down here as well. It's going to end up looking like this, right? But for our purposes, we're only doing kind of looking at half of the diagram. But just keep in mind, this is the true center of the object after it's been rotated. So you're going to start, put your pen or pencil on the dotted line and extend to the furthest boundary that you see. That's going to be your big radius, big R. Okay. Again, start on your dotted line and extend to the closer boundary. That's going to be your little r, small radius. If you put them next to each other, your big R should always be longer than your little r. Okay, so you're never going to have to, I mean, if you put them really far apart, then there could be a situation where the graph curve drastically changes and the small radius looks longer than big radius. But if you put them relatively close to each other, it should be obvious. The longer length will be big radius. The shorter length will be small radius. All right. We see vertical radius. So if we see vertical radius, we're dealing with an easier problem. We're doing top minus bottom. Everything is in terms of x. We're going to be using these functions that they provide for us. So all of our equations will look like y equals on the left side. And these equations are ready for us to use. Y equals x squared, y equals root x. Anytime you see a vertical radius, you know it's going to be an easier setup. Okay. All right, so let's build our 2 radius. we're going to figure out what graph is the top of the radius sitting on, and what graph is the bottom of the radius sitting on, and we're just subtracting them. Right? So the top of my big radius is sitting on the root x. The bottom is sitting on the 0. So root x minus 0, which is just root x. Okay, my small radius, I'm just looking to see what is the top of my small radius touching, which graph is it touching, and then look at the bottom to see what that's touching, and just subtract them. So the top of my small radius is sitting on the x squared. And the bottom of my small radius is sitting on the dotted line, which is y equals 0. Okay. We're just following the formula for our volume. So v is equal to pi, depth integral from x sub 1 to x sub 2. We're looking at the boundary of the shaded region. So sometimes your dotted line may be all the way over in a different part of your graph. We don't care about the dotted line if we're talking about the bounds. The bounds is only for the shaded region. So we're going to go as far left as 0 and as far right as 1. And then big R squared. Make sure we're squaring our big radius separately from small radius. Okay. Let's practice putting this into our calculator. I like to store. I know this doesn't seem like a big deal right now, and you can put it all into your Math 9 line. But I like to practice or get into the habit of letting y1 and y2 hold my big R and little r, just because later on your big R, little r is going to get extendedly more complex, and it's just nice to kind of separate it so there's less parentheses involved. So my y1, I'm going to have root x, my big R, and then my y2, I'm going to let that be x squared. Okay, Math 9, go from 0 to 1. I'm leaving pi out of my calculation again, just because I know I can just attach that at the end. And then alpha trace, I'll call my big radius and then square that, minus alpha trace y2, square that, and then dx. 0.3 is same thing as 3/10. Both are fine. Both are exact values. So my volume is going to be 0.3. Don't forget about pi, and then units cubed. Any questions? All right, example 2. So I do want to point out a common mistake that students do make is doing this, okay, where they draw the distance between the two of them and they call this either big R or little r. So if we have the washer method, make sure we don't do this, right? I mean, this is good for area, but this is not good for volume. So this is basically doing this from a two-dimensional perspective, right? If we're connecting the region, then we're calling this the radius, and we know that's not the radius. So make sure that whenever you draw your big R and little r, that you're always involving the axis in building your radius, right? You always have to involve the center if you want to call something the radius. All right, example 2. Find the volume of the solid created by revolving the function y equals x squared plus 1. I forgot to include the other function here, and y equals 2. I'm sorry, I did put that here. Bounded by the line y equals 2, revolved about the x-axis. Okay, so I did have that. So we have our shaded region that's going to be created with these two graphs, and then we're rotating this shaded region around the x-axis. So we have y equals x squared plus 1. That's going to be a parabola that opens up at 1. So there's my parabola, y equals x squared plus 1. That's y-intercept at 1. Bounded by the line y equals 2. So here's our shaded region. And we're rotating about the x-axis. So x-axis is down here. So imagine rotating this around this line. It's going to end up looking like a weird shaped ring, a ring that is kind of curved on the inside, but then kind of flat on the outside. But again, don't have to worry too much about visualizing or even drawing these graphs. We just have to be able to figure out, okay, is it this method? Is it washer method? Do I need to do 2 radius or 1 radius? And here, if you look at the dotted line versus the shaded region, it's not even touching. So if it's not even touching, it can't be this method. So it's got to be a washer method. Now, even if it were touching, it's still up against a curved surface. So this curved surface, even if the dotted line was up here at y equals 1, it'll still be washer method. So I want to make sure that we understand these two are both washer methods, right? Whether it's touching or not, can both be washer method as long as your shaded region is a curved surface, right? So if it's flat surface touching the dotted line, that's the only time that you're going to have this method, right? So I think a lot of students want to do this. They want to say, oh, if it's touching, they think, oh, touching means this method, not touching means washer method. It's a little bit more than that. Okay, it's more about the curved region, whether it's curved or flat. Right, but this one is obvious. This one is going to be washer method. So from your dotted line, you're going to extend to the furthest boundary, and you're going to call that big radius. Okay. From the dotted line, extend to the closer boundary, and that's going to be your little radius. Notice both your radius are involving the dotted line. Right. You're going to be tempted to want to connect the distance between the two boundaries, but this is not the radius. All right, so big R and little r. All right, let's name all these graphs here. So this is y equals 2. This curve is y equals x squared plus 1. Okay, so we're adding these infinitely thin circular rings from one end to the other. And this one requires us to find the boundary on our own because we can't really tell by looking at the graph whether, what these x values are. But we need these x values because these are as far left and as far right as our graph goes. So let's find our boundaries, find our bounds. We're going to set the equations equal to each other. So we'll say x squared plus 1 is equal to 2. We'll set the curve equal to the line. Take the square root. Right, so we have left bound is -1, right bound is 1. So let's go ahead and build our two radius, big R and little r. So look at your big radius. Look to see what is the top of the radius sitting on. Top of the big radius is sitting on this horizontal line, which is y equals 2. So top minus bottom. Look at the bottom of radius. Bottom of the radius is sitting on the dotted line. So that's 0. So 2 minus 0 is 2. All right, little radius, look at the top of little radius. It's sitting on the boundary x squared plus 1. And the bottom of radius is sitting on the 0. Okay. Everything we need is in front of us. We can now put into our volume formula. So from -1 to 1, big radius squared minus little radius squared. Okay. I'm going to y1 and y2 and calling y1 my big radius, calling y2 my little radius. And you can probably use the setup that you already gathered from that you've already built. You can just go up, call that same function. Really, the only thing you have to change is the bounds because you already have your y1 and y2 holding your big R and little r. So that can save time. You don't have to do a whole bunch of re-entry because you already have your washer method formula set up. You just have to adjust the bounds. I like to do math fraction to see if it will convert into a fractional value. If it's not able to, because it's too complicated, then you can just leave it in this form and round to 3 decimal places and then add pi at the end. All right, questions? I do want to point out another common mistake that I see students make is some students would do, they'll do big R minus little r, and they'll square it all together once. So make sure that's different than squaring them separately. So make sure that you're squaring your big R and little r separately, and that you're not just doing big R minus little r and just squaring all at once. And that's not the same. So we need to make sure both your radius get their own squared. Both gets their own squared exponent. All right, next page. Okay, I want to skip example 3 and talk about example 4 because we know that the more challenging ones is always if we have right minus left, right? Top minus bottom. It's a good way to introduce us into the concept, but we know the more involved problems are going to be where we have a vertical axis and a horizontal radius, because the equations are going to have to be rewritten. So we have find the volume of the solid. We have the same shaded region though, but now we're revolving about the line x equals -2. Now x equals -2 is a little bit off the grid here, so I'm going to extend my graph here and count to -2. It's not to scale, but it's okay. And then here is the dotted line. And then my axis of revolution is all the way over here at x equals -2. So what's going to happen is this is going to get rotated around this line. It's going to end up looking like a weird, I don't know, like an upside down lampshade maybe. But obviously there's a huge gap. We know it's going to be washer method. And also, if you look, there is no flat surface at all with the shaded region, right? So no matter where the axis is, even if it's touching, it's always going to be washer method, right? So if you see a shaded region that has no flat surfaces, you instantly know it's got to be washer method, because we're never going to be able to create a flat surface up against the dotted line. Okay. So you got to have a flat surface and the dotted line up against that flat surface in order for us to make it this method. So we have our axis going vertically. We know our radius is always going to kind of form a T with that axis. So you're going to put your pen or pencil on your dotted line. You're going to extend to the furthest boundary that you can find, and that's going to be your big R. We're going to call that big R of y, since right minus left. I start on the dotted line again. We know there's a hole that we have to subtract out, and that's going to be your small radius. Extend to the closer boundary, the boundary that takes less distance to get to, and that's going to be the length of your little r. And again, your big R is always going to be longer in length than your little r, assuming that you're putting them relatively close to each other. The red flag that comes with anything horizontal, whether it's horizontal radius or horizontal length, is that your equations are not in the proper form. We have to take the time to rewrite it and solve for x. So this parabola is now going to be x equals square root of y, because I have to solve for x. So to undo that square, I have to take the square root. So this curve is going to be x equals square root of y. Let me use a different color. You can see. All right, this other equation, root x equals y, if I solve for x, I would square both sides. So x equals y squared. So x equals y squared is going to be this other curve that formally we call y equals root x. All right, let's build our two radius, big R and little r. So big radius, look at the length of your big radius and look at what it's touching. What graph is the end of your big radius sitting on? It's sitting on this y equals x squared, but we can't call it y equals x squared anymore. We have to call it x equals root y. So right minus left. So root y is the curve on the right. And then you look at the left endpoint of your radius, which is sitting on the -2. Careful here. It's right minus left, so this minus is different than this minus. We have to include both minuses. One is the subtraction between the two, right and left, and the other negative is coming from the left itself. So just careful and keep track of your negative there. It's going to be root y minus a -2. Which we can rewrite as root y plus 2. Okay, little radius. Right minus left. You look at the right endpoint of your little radius is sitting on the radical function, which we have rewritten in a form that's better suited for our problem. So which is y squared. So y squared minus a negative 2, right minus left. Next up, we have to involve the boundary because there's boundary involved even if we're doing right minus left. But now we're stacking these circular rings from the lowest y value to the highest y value. And we see the lowest y value is 0 and the highest y value is 1. Remember, you're only looking at your shaded region for your boundary. You may be tempted, oh, wait, what about this axis? Does this axis have some impact on the bounds? It doesn't. Okay, so remember, you're only looking at your shaded region for your bounds, whether it's area, whether it's volume. It's only the shaded region that you care about. We don't worry about the axis. The axis is only going to impact your big R and little r. It's not going to impact your bounds. So we're going from -1 to 1. Sorry, 0 to 1. Lowest to highest y value. And big radius, make sure you square your big radius. Minus and each gets their own squared exponent. Okay. I'm going to call the root y plus 2, big R, and the y squared plus 2, my little r. And in your calculator, we're only using what variable? X, just use X, yeah. So yeah, all you have to do is go to y1 and y2, update your big R and little r, and you can call the same line that you've already created. It should be pretty fast. Okay. Root x plus 2 being my big R, x squared plus 2 being my little r, going up to my previously called expression. I'm going to reuse that because I already have everything set up for washer method. The only thing I have to adjust is my bounds. My lower bound should be a 0 in this case. Let me see if this will convert to a fraction for me. It's not able to convert to a fraction, which is okay. Then just round to 3 decimal places and then attach pi at the end. Right, how to differentiate them. If you put them relatively close to each other, your big R is going to be always longer in length than your little r. Oh, got it. Yeah, it's always going to be big R first, followed by little r. Does that make sense? Or are you talking about which? Oh, you're talking about how do we build these equations, or how do we build big R and little r? Mm-hmm. I can maybe help you at the end. Okay. So, uh, so let's go to page 16. Let's see if we can do 2 problems. I would like to do a problem where we do a top minus bottom and do a problem that's right minus left, so we can kind of see, just get practice with those 2 variations. So page 16. Try A and then try B. Okay. I'll put the answers up in a little bit so you can kind of we can kind of check our progress. Oh, the additional complexity with this problem is that it's going to be kind of tough to solve this by hand and get an algebraic answer. So you may have to go to your calculator and actually find those intersections in order to find your bounds. Okay, so we did this on the second day when we did area, right? So you're going to graph these two functions, natural log of x minus 2 and x minus 4, and then go ahead and find both the order pairs at those points, because even though we're using x values here, we're going to be using y values here. Um, x equals y squared. Well, if you look, the r extends all the way to this curve, which is y plus x squared, which is x equal to 1. So root 1 minus that equals 2. That's it. It'll match with this y plus root x, which I'm reading about is and then y squared minus. Nice. Let's see if you can manage it. Okay, so first is we have the shaded region. Oh, if you look, this, I know you may be looking at this, and this looks like a flat surface. Okay, how about this? It needs to be a flat surface that's either horizontal or vertical. It needs to be perfectly horizontal or vertical. So let me be more clear there. So this shaded region can never experience this method, right? So even though technically this is a flat surface, no matter where you draw the axis, your axis is always going to be either horizontal or vertical. So let me update my statement. You're only going to get a possibility of this method if one of your boundary is a vertical or horizontal flat surface. So, but this one, I know the axis is completely off the shaded region, but just wanted to point that out. Our axis is all the way up at y=2. There's obviously a gap. And even if it were touching, it would still be washer method. And then we extend from the axis to the two boundaries of the shaded region, and that's going to be your big R. I know this looks like the edge of the diagram, but it's really at the center because this is going to end up rotating around that axis. That's going to create like a weird shape with a gap in between, a hollowness in between. And then we do top minus bottom. So top is sitting on the 2, the bottom is sitting at the x-4. And careful, whenever you have multiple terms following a minus sign, protect that with a set of parentheses. Otherwise, it's not going to be correct because the negative has to distribute to everything that comes after it. So 2 minus parentheses x-4, and then little radius, top minus bottom, 2 minus the curve, which is parentheses natural log of x-2. Clean that up. My big radius is 6 minus x. My bottom radius is 4 minus natural log of x. And then to find my bounds, I need to set the equations equal to each other. I think it's easier to use your calculator and then do, you're going to do second trace intersect, find points close to those intersections, and you should be able to nail down these points here, 0.1586 and 3.146. Now, as you find those points, go ahead and identify their y values, because those y values will come in handy when we're rotating about a different line. I mean, I think the nice thing about this unit is if you can nail down your setup, then you basically have the answer because the rest is just calculator. Yeah. Oh, the volume here? Yeah. I got positive, and also our volume should always be positive. So let me see if I got that mixed up. Point 1586. Oh, 6. I got positive 16. Let's see. Okay. I had my big bar being 6 minus x, so it's got the, which isn't a big deal because you basically have the answer. You just have to change the sign. All right, let's try part B. Anytime you see a vertical axis, you know your radius has to be horizontal because you're always going to get that T-shaped relationship between your axis and your radius. And obviously there's a gap, and we're going to have to draw our big radius and little radius. But you know that these problems are going to take more effort because these equations are not in the proper form. So The equation was y equals x minus 4, but that one's a little bit easier to rewrite. We can simply make it x equals y plus 4. Again, you're not just swapping x and y, you're actually solving for x. So you got to, do some algebraic steps to get there. And the next one is y is equal to natural log of x minus 2. And that one, we have to actually go through some exponential steps here. So first, I would want to get that natural log of x by itself. So I do y plus 2 equals natural log of x. But I want to, this is log base e, right? I want to turn that into x by itself. So I'm going to raise both sides with e as the base. That's the way that we can get rid of natural log. So if I raise both sides with e as the base, e raised to the natural log of x becomes just x. So my log equation in terms of x is going to be x equals e to the y plus 2. Okay, so that adds a bit more complexity because this natural log of x minus 2 is good for top minus bottom, but it's not going to be a good fit for right minus left. Your intersections, I think we can just use our calculator and use the y values that you found. So the y values that you found at those order pairs, the lower y value is going to be negative 3.84, and the higher y value is going to be the 0.853. And then we're going to set up our big R and little r. So big R is right minus left. The right endpoint of my big radius is sitting on the line. The line has been readjusted to a new equation to be y plus 4. So y plus 4 minus a negative 1. Right minus left. Y plus 4 minus negative 1, which really is y plus 4 plus 1, which is y plus 5. And then this natural log graph, if I rewrite it in a different form, it needs to be x equals y to e to the y plus 2. So the small radius is e to the y plus 2, which is the curve, minus a negative 1. So e to the y plus 2 minus negative 1, which is e to the y plus 2 plus 1. And then we just put it into our formula. Big radius squared minus little radius squared. And then our bounds, smaller y value to the higher y value. Lower y value to the higher y value. Again, you're putting y's down on paper, but in your calculator, you're using x's. Okay, your homework, pages 3 and 4 in your packets, which is going to be focused on mainly washer method. I think there may be some disk method in there, but you should be able to tell, right? If your dotted line is up against the flat surface, then you know it's going to be disk method. If it's anything else, it'll be washer method. All right, I'll send out a reminder on Sunday, and I'll also send you a link so you can check your answer as well. All right, come get your phone. Oh, and then if you have time, start looking over your derivative and integral rules, since we're going to have a quiz on that on Wednesday. Okay. Okay, great. Thank you.
I have a question. How do you know that this is for this part, this line, and this is for this line?
So the x minus 4 is going to be a linear graph. So there's no curves, it's just be a diagonal line. Yeah. And natural log of x minus 2, that's a natural log graph. It's always. You can also graph them both in your calculator and see as well.
Yeah.
Yeah.